Hey everyone, I'm giving you some highlights from 8.3. 8.3 is on confidence intervals for sample means. And there's two types of confidence intervals for means based on whether or not you know the population standard deviation. I'll also be showing you the calculator shortcuts during this video. It's much easier with t intervals than it is for proportions, and you'll see why. So the first kind of confidence interval you can make with means is a one sample z interval. So key being z. And to use a z interval, you need to know the population standard deviation sigma. And then you'd have to check your necessary conditions, of course, but to use a z interval or a z score for these intervals, you must know the population standard deviation. So let me go to the calculator cheat for this. So if you go to Menu, Statistics, Confidence Intervals, the very first option is a Z interval. You could put data in. Usually for these, you'll have statistics. So you pick stats. And then you would enter in whatever information's given in the problem. Here's the population standard deviation. This would be the sample mean that you're basing your confidence interval off of. Here's your sample size, and then whatever level of confidence you choose. That's how you would do it if it's a Z interval, meaning you know sigma. So let's say, for example, a problem doesn't give you sigma. They give you a sample standard deviation. Well, you wouldn't know what to put here in this first entry, so you'd kind of know you picked the wrong thing. So just to further emphasize, to use a Z interval for a population mean, you must know the population standard deviation. And you would see the words population standard deviation, or the standard deviation is known to be. And then we had some of these last section with proportions. If you want to choose a sample size given some margin of error. So remember the formula here is X bar, that's your sample mean, plus or minus Z star sigma over square root of n. This is your margin of error. And if you remember from 8.2, this X bar, that's your point estimate. So because the sample mean is not likely equal to the population mean, you can't just say that's what my mean is. Samples are very different from populations usually. You add or subtract this margin of error based on some significance level. So this is your point estimate. Here's your margin of error. So if you're ever asked to calculate sample size based on some margin of error, you're only concerned with the margin of error part of the formula, which is the Z star times sigma over square root of n. The less than or equal to, you don't need it when you calculate. I know in the last video for 8.2, I showed you that sheet in the calculator. If you did a numerical solve. So if I go to Menu, Algebra, Numerical Solve. Let's say I wanted a margin of error within 1. And then my margin of error formula, we'll just say 1.96. We'll just say it's a 95% confidence. I'm just making these numbers up. Times, we'll say our standard deviation is, it should be times. Let's say our standard deviation is 0.025. I'm making this up. And then divided by square root of n. Don't forget your comma n at the end. And press enter. Well, poor example because of my numbers, but our sample size, we'd have to say at least 1 here. Well, I made this up, so it didn't work out too great. But that's how you would type it in the numerical solve, based on some margin of error of the mean. Your Z star is based on the level of confidence. Whatever the standard deviation is of the population would go on top. And then you could numerical solve it for that n, and it will give you your sample size. Now, usually, we wouldn't create a confidence interval if we knew sigma, because then we would probably know mu, the population mean, as well. So usually we'll have to do a confidence interval when sigma, or the population standard deviation, is unknown. And then you kind of think about, well, our best estimate, so what we're going to use for this is the sample standard deviation, which we all know is S. Now, when you use S to make these calculations, you kind of leave your normal spectrum. You're still normal-ish, and it's a special distribution called a t-distribution. We talked about last semester, and the t-distribution looks very similar to a normal distribution. So if you look at this picture, this is straight from your textbook. The purple curve is your normal. So this purple curve here is a standard normal distribution. And if you notice, the red dash curve and the blue curve look very similar to it in shape, meaning they're both symmetric. They're both centered at 0. They both are mounded in the middle, and the area in the tails is less. But notice the area in the tails is a little bit more for these t-distributions than it is for a normal. And really, as the degrees of freedom go up, so as the degrees of freedom increase, the distribution will become more normal. And you can see this in this picture. So notice the red dashed line. The red dashed line has 2 degrees of freedom. Yes, it has a normal shape, but it's not as high in the center and it's higher in the tails. And then if you look at the blue curve, those degrees of freedom are 9. So the degrees of freedom have increased. That means it becomes more normal. And if you see, it's lower in the tails than the red dashed line, and it's higher in the peak than the red dashed line. That'll help with your 8.3 question 1, because they give you 2 curves. It says the standard normal and then a t-distribution with 2 degrees of freedom. So that little tidbit there about the area and the tails in the center based on degrees of freedom, that should help you answer this question 1 from the homework quiz. Let me go back. I think that was the end. Yes. A little bit more about t-procedures. So just like normal distribution have z-scores, t-distributions have something called a t-score. So look at the formula for a t-score. Looks very similar to a z-score for a sampling distribution, except here in the denominator we have a sample standard deviation. Not incredibly important to us because we have a calculator. What is important is the t-distribution. The degrees of freedom are always n minus 1. So whatever that sample size is, minus 1 is your degrees of freedom. That's important in knowing the correct t-distribution. If I go back to the previous slide, you could have many t-distributions, actually infinite t-distributions based on these degrees of freedom. So it's important that those degrees of freedom are correct to get the correct probabilities. Now, how do you find these t-stars without the formula? Well, our calculator is the easiest way. It says you can use technology if you read the directions here. Check your answer with technology. We're just going to use technology. So if I want a 98% confidence interval based on this n, that means if you picture this t-distribution, it looks normal, right? 98's in the middle, or the area is 0.98 in the middle. If I want these 2 t's, this one on the left and this one on the right, they're going to be the same t, because remember, it's still centered at 0, just one's negative, one's positive. I'm going to do an inverse t, not inverse normal, inverse t of this little tail. And the area in this little tail is 0.01. Right? If this is 0.98 and the whole thing is 1, that means both of these tails together are 0.02, which means one of the tails is 0.01. So I go back to my calculator and I do an inverse t. It asks for the area, we says 0.01. Now the degrees of freedom, this is where you have to think. The sample size in that example was 22, but degrees of freedom are defined as n minus 1. So we're going to use degrees of freedom of 21. And there's my inverse t, or my t star, for a 98% confidence interval where your sample size is 22. So if I was making a calculation, that t star would be 2.52. And that's important. I'm just going to do that one, but you could do the same thing for a 90%. Here, your degrees of freedom would be 9. Your area would be 0.05, right? There's 0.1 left over, but half of it's 0.05. So all of these work the same, just based on a different level of confidence and a different sample size. That t-star is important because if you're doing a confidence interval now, there's no common t-stars. So if you remember from proportions, or even if you did a confidence interval for means, that's a z-interval, you would have those common z-stars because a standard normal is just that, it's standard. Those z-scores are the same regardless of your confidence level. With these t-distributions, because their height could be so different, the t-stars are going to be different every time based on the sample size. So you either have to calculate them, or you could use the shortcut in the calculator, and I'll show you that in a second. Let's talk a little bit about conditions first. So conditions to create one of these intervals, the same as last time. There's going to be a little bit special condition for normal with a t-distribution. So these 3 conditions are the same as they were for sampling distributions. I just add in the random. But what's a little bit different about this normal condition for t procedures is that t procedures are something called robust. And if you've been watching the news lately, I've heard this word robust a lot when they talk about studies based on COVID-19 vaccines and testing for coronavirus, all that stuff. You would have heard this term robust. And what robust means is the probability calculations will still be somewhat accurate regardless of the conditions being met. So even if one of these conditions kind of fails, with a t-distribution, the procedure is still good enough if any of those conditions aren't met. So there's a special normal condition for t-distributions. And that is if the sample size is less than 15 and the population is normal. So the data, or I shouldn't say the population, whatever that sample data, if that looks normal, it's safe to use t-distributions. So notice, less than 15, usually we want more than 30. Up here, we want n to be greater than or equal 30. So even if it's not, if the sample data looks normal, we can still use these t procedures. If the sample size is at least 15, meaning n is greater than or equal to 15, we can still use t procedures unless there is outliers or strong skew. So less than 15, maybe the distribution looks a little bit slightly skewed, like slightly skewed to the right here, we're still good to go. Or maybe it's symmetric, but you have one outlier. So maybe you have some symmetric distribution of data, but then you have this little outlier on the end. Well, we're still good to go if it's at least 15. And then for large samples, greater than or equal to 30, just like before, we're good to go. So a little bit unique with that word robust, meaning this condition has a little bit of flexibility if you're doing a t interval as opposed to a z interval. Let me go back to the homework quiz real quick. So here in question 2, to find your inverse t, or find your t star, you're just doing inverse t's. In question 3, little hint for you, notice they give you sigma, the population standard deviation. So they tell you, well, here's my sigma. That means you're doing a z interval, either in the calculator or using the formula. And then the last question, here you're giving some sample data. So this is from a sample. So it's kind of shouting at you, well, this is probably a t distribution. So down here, you would be using a t interval. And real quick before I run out of time, in the calculator, if you did a t interval, here is where you would pick data. I'm a little ahead of myself. You would have to enter this in a list and spreadsheet. And then the shortcut is you can go to data, t interval, pick data, and then pick whatever list you typed in and your level of confidence. I hope this helps with